It was concluded, from what I understand, fairly recently. So it is very appropriate that a member of that institute is being invited to give a public talk at this function. With that remark, I am supposed to pass it on to Jam, so I'll do that.
Thanks. Thanks for passing it on. I was desperately waiting for the mic. Yeah, okay. So we have 2 public talks, and with that, we'll end the Golden Jubilee celebration. But before that, we just wanted to take a few minutes of all your time to thank all the people who have made this whole Golden Jubilee celebration possible. On behalf of the organizing committee of the IMSC Golden Jubilee celebrations, it's my pleasure to thank, firstly, all the speakers who have come here and made this possible. And I would like to thank all the alumni who have come from various parts of the world to be with us during this period. I would like to thank all the session chairs who have, including Bal, who gave me this chance. And the compeers like Professor Simon and Professor Bhaskaran, who conducted the proceedings for the reminiscences sessions. So all the compeers. And I would also take this opportunity to apologize to any alumni that we had missed out in the organization for a variety of reasons. There are 1 or 2 non-trivial examples, and we apologize and hope that we will complete our database and keep in regular touch with alumni from now on and find systematic means for doing so as well. And then the administration. I think the administration has played a tremendous role, not just for this particular meeting, but all through the year. We have had a series of Golden Jubilee events and various activities in the Institute, and the administration has played a tremendous role in this, and we would, the organizing committee would like to thank the administration for doing this tremendous job, all the volunteers who have taken this effort, and I believe the director has a little more to say on this.
As we approach this concluding session, it is time. Yeah, and I would think it's rather very well, superbly organized event, even if I may say so. And it is time that we acknowledge the contributions of the various people towards the organization of this. And particularly first the organizing committee. The organizing committee, Professor Ramanujan, Murthy, Date, Krishna, and Meena. And I would assume that all of you would have known whom they are. But in any case, I may request them to stand up so that the people would know who have been. Responsible for such a great event. No such event can take place without an adequate support of the administrative staff, and as Jam was already mentioning, we had not only this event, but there have been a lot of events, and the administration has helped a lot in organizing all these events. And we have been more or less taking them for granted, and they have done a fantastic job. Therefore, let me mention the name of a few of the administrative staff, and since it's a little long name, I might forget 1 or 2, and then probably you should also see who are the administrative backbone who did all these jobs. And this would include Jayaraj, Gayatri, Indra, Shankaran, Vasudevan, Parthiban, Srinivas Raghavan, Parijatam, Usha Uttiswaran, Geeta, Ahmed, Mohan, Arangarajan, and from the computer side, Subramaniam, Ravindra Reddy. Then again from the office, Johnson, Prema, Vidyalakshmi, Padmanabhan, Gopinath, Sundarlingam, Shivaraj, Agilan, and from the library side, Pandian, Venkatesan, Usha Devi. All of them have done their best to make this as a great success. Can I ask them to stand up so that and finally, we give to the one person who has led a team of all these people and has worked day and night beyond his call of duty, and he has made all these people work day and night beyond his call of duty. Otherwise it would have been possible at all. And this is that one which he is not only doing for this particular conference, but for all throughout this conference. And we would like to express our appreciation by giving a small memento to him, Mr. Vishnu Prasad.
Sirs, thank you very much for the freedom given to us to work along with you day and night to make this function a grand success. We are thankful to the organizing committee and Director IMSC and all the faculty members and staff members of this institute, and my colleagues especially. Thank you very much.
I am glad to be given this opportunity to introduce you to Rafael Sorkin. Okay? He is undoubtedly one of the oldest physicists in terms of my collaboration, which goes back to the 80s when we joined Syracuse University, and when we worked together very strongly for many years. But he may not know it, but I knew of him even before that, because I heard of the adventures that he and John Friedman had in getting arrested in anti-Vietnam protests, and the interesting conversations they are supposed to have had with Chandrasekhar in Chicago. Okay? Now, he was in at some point in Syracuse, he was, took leave and went to UNAM in Mexico for 2 years. And I suspect that if there is a popular demand, he can easily switch languages and give this talk in Spanish. No, obviously, no. In Mexican Spanish, probably, with lots of vale and cabron, which I will not translate. Okay. Then he came back to Syracuse, and eventually he has gone to Perimeter. Okay. But I should also mention that he has a very strong Indian connection. Fatma, his wife, which I don't know whether she is here. Okay. I don't see her. Okay. Huh? She is from Zanzibar, so, and she is the, I think, granddaughter of immigrants from Gujarat. Okay. And not only that, he has an ongoing collaboration with Sumati Surya in RRI in Bangalore. And of course, he has, we have kept in touch with each other on many physics matters and other matters for a very long time, even continuing to this day. Okay. I should say that I have learned a lot from him. Okay. As I said, I was very excited when he turned up in Syracuse, and it was not fruitless. I mean, he taught me a lot, especially on many of the intricate aspects of quantum physics and the nature of space-time and the importance of mathematical ideas in conceptualizing many basic issues in physics. Okay? He has had a passion, I should say, from what I know, about the nature of space-time for a very long time, from what I have seen. Okay? I should say especially quantum space-time, which all of us believe is completely different, not all. Certainly I believe is totally different from what we imagine by looking at this room. Okay? In particular, we know already from looking at ordinary quantum field theories in Minkowski space that causality and locality play a very important role in the formulation of the theories. But what these things mean when you go into quantum gravity, we have no clue really. Okay? We have no idea even what is meant by a local observable in quantum field theory when you introduce quantum gravity. Okay? In this respect, he has proposed the idea of causality, a particular model for incorporating causality, and maybe it also has in this as an ingredient the notion of locality, but that is not clear. Okay? He likes to quote, I see some mathematicians in this audience, so he likes to quote constantly Riemann from his habilitation thesis, where he already speculates or rather makes precise statements about how our present space-time may emerge from a discrete structure by counting. Okay? And I believe that this has been an inspiration for him in his research for the past nearly 20 years on partially ordered sets, of which he will tell us something now. Okay? Recently, he has done some very important work, which some of you may know, namely how to quantize quantum fields in arbitrary metrical backgrounds in finite space-time regions when you may not even have the notion of Cauchy surface or Hamiltonian idea at all. Okay? This activity actually is, in some way, is not new. People have discussed what are called Hadamard states, but he has had a variant of this, which is extremely interesting and very simple, and I suspect that it will have consequences in areas which beyond what he imagines, I suppose. Like, for example, mesoscopic networks. That is my suspicion. Okay? All right. Our interests diverge at one point, but it is seems to be converging again. Okay? So, in this context, I am reminded of this, a quotation from Haag's book, which some of you may know, on local quantum fields, where Haag talks about the predetermined harmony between physics and mathematics. He sees that developments in mathematics and developments in physics, which you thought were totally different, seem to converge again and again as you keep going. Okay? And I believe that Hilbert, in one of his, in this long talk where he proposes how many problems, 27, 28, whatever, he talks also, he speculates also on this issue of how it is that these different enterprises, apparently different enterprises, done by humans, seem to converge again and again. Okay? Now, our interests have diverged, but in the same way as Haag says, there appears to be a predetermined harmony in the way they seem to be converging every few years. Okay? For that, I am very happy. Okay? Now, I will finish this thing. Okay? As people say, switch off your mobiles, and undoubtedly, many of you eat chewing gums. Then unwrap them now. With this, I present you Rafael.
I guess I should. So I want to first thank Baal for that wonderful introduction. But he left out my most important Indian connection, which he's probably not aware of, but the one of which I'm most proud is that I'm now officially a person of Indian origin, which allows me to travel back and forth, and hopefully this MOU implement it without having to get a visa each time. Is this for some reason not showing up? Let me see. Oh. Okay. And like everyone else, someone has left their glasses, and it looks a lot like mine, but it's not mine. So, here we go. So, yeah, so like everyone else, I'd like to thank the organizers for this wonderful conference, and to say how happy I am to be in Chennai, which is actually, although we've been in India before, the first time we've ever visited the city, and I get the impression of a very warm, friendly, welcoming kind of population here. So what I'm letting you look at while I talk is a picture of a causal set. Maybe I should actually, since it wasn't visible, maybe I should let you look at the title for a few seconds. So gravity from order and number, causal sets. I'll try to explain, of course, what that means in more detail during the talk. But the picture that I thought would actually be up while we were waiting for the talk to start is a causal set that was generated by a process called transitive percolation. Transitive percolation is a special case of a more general family of processes called classical sequential growth. And in fact, it's generated by a growth process, a process in which these elements come into being one by one. And that's how we like to conceive the dynamics of causal sets, which would, if causal set program comes to fruition, will be the dynamics of space-time itself. However, the classical sequential growth process that I just referred too, as its name makes clear, is a classical and not yet a quantum process. If it were quantum, and if it were the true dynamics of the causal set, then you might be looking at the first 4,096 elements of the universe, or more likely, the first 4,096 elements to come into being during the most recent cycle of expansion of the cosmos, the one in which we are now. So this is just to give you a flavor of what a causal set is. I'll define it somewhat more precisely a little bit later. Before doing that, let me list some collaborators who have been involved in this work. Actually, not all here now, but most important ones are listed. And let me also say that in this, I had originally thought that I would concentrate mostly on causal sets in this talk and give just a brief introduction to quantum gravity, but understanding the nature of the audience better. And so I think that maybe today a more appropriate thing is to concentrate a little more and dwell a little more on the problem of quantum gravity in general, just to give you an idea of what it is and how I see it. Because of that, I think I will have to not quite get to the end of some of the things I would have said about causal sets. However, I will certainly try to say some things, in particular to give at least some flavor of the recent progress that has taken place in that program. But if you're interested in learning more, let me give you these references. So these 3 references are all available on the Perimeter Institute website, what's called PIRSA, Perimeter Institute Perimeter Institute Recorded Seminar Archive, which is available from their main homepage. And there's 3 things. There's a mini course of the duration of about a week that Faye Dowker and I gave, introducing the idea of causal sets. There's Joe Henson's invitation to the mini course, which was called An Invitation to Causal Sets. That's also on PIRSA. And then for those of you who are not interested in a more technical treatment, there's the public lecture that Faye Dowker gave as part of the public lecture series on science in Perimeter, that Perimeter Institute holds every month. That is available on both YouTube and on PIRSA. So as I said, I want to dwell a little bit on the meaning of quantum gravity, or the nature of the enterprise. Before I do that, let me say in what way causal sets, I think, fits into this whole enterprise. And it's given here in I don't know why it does that. It's given in a sentence. Among the various ideas put forward in the search for a theory of quantum gravity, the causal set hypothesis is distinguished, I would say, by its logical simplicity and by the fact that, in contrast to most other approaches, it incorporates the assumption of an underlying spatiotemporal discreteness organically and from the very beginning. And I hope by the end of this talk you'll have a sense of why I'm saying that. But let me now go back to the question, the more general setting in which the causal set program proceeds, which is that of the problem or the question of quantum gravity. So if you ask what is quantum gravity, I've said here that the short answer is that it's a whole lot. This is a quotation from an indigenous artist in Australia who apparently was asked by some sort of journalist what her art was all about, and this was her answer. So aiming to emulate an artistic approach, perhaps in physics, we could say that quantum gravity is about a whole lot, and here is some of that whole lot. So like I've organized this thing in sort of 3 parts because I think that a useful way of thinking about physical theories, which was actually proposed by the Japanese philosopher of science and physicist Mituo Takatani, is to think of a theory as having 3 important facets, what you might call its kinematic facet, its dynamic one, and its phenomenological one. He used some Japanese words which were probably translated wrong from what I've read, so I won't try to reproduces terminology. But this is a familiar way of thinking to physicists. By kinematics, we really mean what is the theory talking about. By dynamics, we mean what are the laws of motion that govern the behavior of those things. And by phenomenology, of course, we mean those directly accessible experiences, experiments or observations that allow us to make the theory to make contact with reality that's accessible to us. So in the case of quantum gravity, the kinematic question, I would say, is this one. What is the deep structure of space-time? This is the very basic and first question that Bal referred to, that you have to answer almost before you can get started. In particular, we can ask these questions. Is it continuous as the shallow structure of space-time is? By the shallow structure, I mean space-time as it's presented to us by general relativity, which is, of course, a deep structure relative to Newtonian mechanics, but presumably a shallow structure relative to quantum gravity. So is it continuous, or on the other hand, is it discrete? Is it perhaps nothing new in the sense that the deep structure and the shallow structure coincide, or is it perhaps some other kind of thing that can't be directly characterized as either discrete or continuous? Here I'm thinking, for example, of, just to make a possible example, non-commutative geometry. If it is discrete, and that's certainly what Causal Set is postulating, what kind of discreteness is it? Is it more like a crystalline discreteness, very highly ordered, or is it more like a fluid, in some sense, locally disordered? Also, if we start with something, a deep structure that's not the same as the shallow structure, not that of a space-time with a Lorentzian metric on it, how does this deep structure produce a continuum, a manifold, together with its metric? I'll claim here, although I might not have time to explain why, that this is very closely connected to, in fact, it can be regarded as an extension of the question of why the cosmological constant, which is what this symbol lambda stands for those who are not physicists, why the cosmological constant is so small. Another question, which is raised already by Riemann in the Habilitationsschrift that Val referred to, is why is there any notion of length at all in physics? After all, we heard yesterday about conformal field theories. They don't have a fundamental notion of length. But in reality, there is. Atoms come in one size and not in another. Why is that notion there? Why is that notion there? And connected to this is the question about the metric. Is the metric a field like any other, to be treated just like any other? Or does it perhaps have some special connection to the deeper physics? So these are what I would call some of the important kinematic questions that arise in relation to quantum gravity. Once you have a kinematics, then there's the question of the laws of motion. So if the kinematic question is what is the deep structure of space-time, the corresponding dynamical question is what are the deep laws of motion that control or influence the behavior of that structure. We talk about quantum gravity, but should these laws actually be quantum mechanical? When we say quantum gravity, all we really mean is some theory that successfully fuses gravity or general relativity with quantum mechanics. It's possible, of course, that it could, in the process, transcend both of them. But if we assume that they are quantal, then we should ask a subsidiary question, which is, in what way are they quantal? One is familiar with different ways of conceiving of a quantum theory, and the two most important, I would say, probably most people would agree, are in terms of the Schrödinger equation, which is some sort of quantum generalization of Hamiltonian evolution on one hand, versus a path integral formulation on the other hand. It's also possible that the laws of motion, meaning the dynamical laws of the theory, would take another form. For example, probably everyone here, even including both physicists and not physicists, is somewhat familiar with the two-slit diffraction experiment, which is in some way the hallmark of quantum mechanics. So as you know, in the two-slit experiment, you have, say, a source of electrons, and then you have, say, a detector, and between them you have a screen. with two apertures in it. And if you block off one of the apertures and you generate these electrons, you'll find a steady stream of electrons arriving at the detector. You then open the second aperture so that both are now open, and suddenly you find that the detector falls silent. No electrons are arriving. Somehow the availability of that second alternative to arrive at the detector has blocked the electron from going by either path to the detector. This is why it's given the name interference. But what's characteristic, and this is completely characteristic of how quantum mechanics differs from classical physics, but what's also characteristic is that the interference in this case is between two paths, and what's characteristic, you might think that in general there could be a new interference that comes in when you open up a third slit and a new type, four slits and so on. What's characteristic of quantum mechanics is that there's only the second order, this two-way interference, and nothing beyond that. This is actually another form of Born's law, or closely connected to Born's law, and it's actually something that you can look for if you're looking for post-quantum theories, and it has been looked for in the Institute of Quantum Computing, and limits have been set on this third-order interference. But it's possible maybe that quantum gravity would need some post-quantum, some higher-order interference, or maybe it would actually need something more radical. This is just one possibility. So to these questions, the causal set has an answer. It proposes a particular answer, just as the kinematic questions, I didn't state the answer that causal sets proposes. I showed you a picture of it. The technical language is that the deep structure is that of a causal set, where a causal set is defined as a locally finite partial order, which you can think of as a kind of generalized family tree. I'll go into that in a little bit more detail later. To the dynamical question, the causal set answer is, well, at least the most conservative thing we can try is to use still quantum laws, quantum mechanical laws, kind of dynamics, but one necessarily based on histories, that is something like the path integral, which, as you may know, is also referred to as a sum over histories. Something that's based on histories and is a kind of path integral, but a somewhat less familiar kind of path integral, which assigns amplitudes not only to individual history, not to individual histories, but rather to pairs of histories jointly. This is called a Schwinger-Keldysh type of path integral. So all these questions that I just raised are dynamical questions, as I've been saying, but there's another question that's neither dynamical nor kinematical, which is what's the relation between the two? I put this here because it's just something one might hope for. I have no concrete suggestion how to carry this any further, but you might hope that just as the history of physics seems to show progressive unifications, that ultimately it will it will erase the distinction between kinematics and dynamics. In other words, it will unify them. That just as there can be no dynamics without a kinematics, maybe the kinematics should, when properly understood, incorporate the dynamics. In this case, this division that I've made would be artificial, but that would be a wonderful, I think, conceptual advance for physics. I just raised that question here. Somewhat related to that question is one which I think that this question, quantum gravity may not have to answer. It may be premature to be raising it at this historical stage. But the following question I tend to think quantum gravity will have to answer, which is the question about the interpretation of the quantum formalism. The best interpretation that we have now is that of the Copenhagen school, which relies on external observers, agents who are outside the system. Many people have been unhappy with that, and in the context of quantum cosmology, it seems to make little sense. So we have to raise the question whether there's some sort of more intrinsic, as I would call it, way of grasping microscopic physics, of dealing with it directly, and not just with what some sort of observer will observe by some undefined process called measurement. In other words, the question is, are quantum foundations intertwined? I tend to think that they are, and that quantum gravity in return might have something to contribute to the understanding of quantum mechanics. Okay, so finally there should be the phenomenological questions, but here, before giving them, I want to list a few briefly who don't fit so clearly into either category, but are also important. First of them is how to describe non-gravitational matter. In other words, other things than the gravitational field, which we know exist, in particular fermions and gauge fields. And here I've committed a sin that I often accuse other people of committing, which is I've left out the Higgs field, which I certainly shouldn't do this year. Or presumably next year, unless some real surprise happens at the LHC that we're not expecting. So fermions, gauge fields, Higgs field, how will we describe that in quantum gravity? Can it happen that these fields somehow are there without our realizing it, that they arise spontaneously? Or must we just put them in by hand, just as we put in the metric field by hand when we're doing, even the metric field by hand, when we're doing general relativity? It was another thing that Bal referred to in relation to Riemann's comment, famous, I think, comment that in a continuum theory, the metric has to be added in by hand, whereas in a discrete theory, it's inherent in the structure of the manifold itself. And we'll see that in connection with causal sets, and that's indeed part of the motivation of the theory. Another question is about topology change. Is it necessarily part of quantum gravity? For example, if we want to describe the birth of the cosmos, where we're going from nothing to something, that's a very radical change of topology. Technically, it can be described by what's called a cobordism. There are also, this is something that we have worked together very much, that is Bal and I, topological geons, which are particle-like excitations of the space-time topology. If they are to be pair-created, again, the topology must change. So is topology change a necessary part of the theory, even at the classical level, and even more so at the desired quantum level? If you're dealing with, say, QED or QCD or any standard quantum field theory, the notion of the value of the field at this particular space-time point is well defined and is a completely local quantity. And it's normally in terms of those local quantities that we construct all observables, or all, if I would use Bell's word, beables, all quantities that have a meaning in relation to in the physics. Or if I were to use the mathematical language, they might be called invariants of the theory. But this is exactly what is not possible in the case of gravity because of diffeomorphism invariance. So if you ask what's the value of the gravitational field at this particular point, it has no meaning because there's no independent way of referring to this particular point except through the values of the fields and the other physical objects at that point and in its neighborhood. Therefore, it's a vicious circle, and the only way out of that is that the observables are inevitably non-local in nature. And that is, in fact, how they are, even in classical gravity. But the problem of implementing these quantum mechanically is a whole new problem, which I would venture to say has been actually solved in the case of causal sets. In fact, it's related to the question I asked Ashok yesterday, whether the ADS-CFT has some way of coping with this. But I would venture to say that the causal sets do and have essentially solved this problem. The last problem I'll just not say much about. It's more of a philosophical nature, but it's hard to describe in a short time. But it's whether or not we should think of the world as a four-dimensional being all laid out like a movie, or whether there's actual change and things really happening in the world. Okay, so I'll now to the phenomenological questions, which are the ones, of course, by which we would have a hope of verifying any particular theory of quantum gravity. So a good thing to notice here is that the list is actually not as short as you might have feared. You might fear that it's very short because the characteristic length scale at which we expect quantum gravity to be important is what's called the Planck length. That's a very tiny length of about 10 to the minus 32 centimeters. If we express it as an energy, the kind of energy that some super LHC in the future might aim at, I think it's some 15 orders of magnitude greater than what we have accessible now. That seems pretty hopeless. Although if you think about how many orders of magnitude in the last century we've gone up, it doesn't seem as hopeless as it would otherwise. I think they're roughly comparable, in fact. But still, we don't necessarily I don't want to wait a century. So are there some things, and it may be much longer, of course, are there some things which we can point to now which have the hope of being detected, which could represent the phenomenology of quantum gravity, either if it's the fundamental discreteness, if that's the right story, or the dynamics, or some combination, of course. The first one on most people's list would again be about the cosmological constant. The question used to be, why is it 0? The question is now even more difficult to answer, which is, why is it so small without being 0? I said before, and I'll say again in red, that I think this is closely connected to, in fact, it can be regarded as an extension of the question of why we get a continuum out at all, as some effective theory, effective object that describes the deeper, possibly discrete reality. Another question is about the role of non-locality. In the causal, we'll see in the causal sets, I believe that's closely connected to the cosmological constant and the mystery of why it's so small. But it's also crucial for causal sets because, as I'll try to indicate, causal sets are radically non-local in a certain way. And one would expect this non-locality to survive in some form on much larger length scales, and maybe we can observe it. Another question that people often raise in connection with quantum gravity is, why is the dimensionality of space-time 4? In fact, if we heard yesterday that maybe it really isn't 4, maybe it's really 10, or maybe in some sense 11. In that case, you have to explain, just as explain why the cosmological constant is so small, why do we seem to get 4 dimensions? The causal set can actually produce a space-time of any dimension, although it takes more and more elements to produce higher dimension. So in practice, we're probably limited to dimensions under 150 or something like that. But still, that's a lot bigger than 4. So why is the dimension 4? Another question that's always puzzled me, although you don't hear it asked very often, is why isn't space-time full of holes? So if we take a classical space-time, which is a solution of the Einstein equations, and we just punch a lot of holes in it, it's still a solution of the Einstein equations. What's wrong with that? Is there some dynamical reason or some basic principle that would forbid that as a solution? There's another question in connection with black hole entropy. As many of you might know, will know, and I'll mention for the others also, that the black hole has a surface called a horizon, and it seems there are many indirect arguments that imply that it carries an entropy proportional to the horizon. In fact, it's roughly equal to the area of the horizon in Planck units, where a Planck unit is a Planck unit of area. Remember I said the Planck length was 10 to the minus 32 centimeters, so the Planck area is roughly 10 to the minus 65 centimeters squared. Where is that coming from? What is the entropy actually counting? Is it something like the entropy of a gas, which to a first approximation is just counting the number of molecules in the gas? And if so, what are these molecules? And then this is really a question about black hole statistical mechanics, if you like, or what you might call the statistical mechanics of black hole thermodynamics. And that has, of course, if you think to ordinary thermodynamics, then more important in some sense even than counting things to give the origin of entropy is to understand why the entropy is always increasing. This is called the generalized second law in the context of quantum gravity, and it raises whole new problems because the theoretical framework in which people try to explain this for classical or non-relativistic thermodynamics is really not there in quantum gravity. In particular, the notion of time gets much more complicated. Speaking of black hole entropy, Hawking radiation is closely connected to that, and then the question is, if there's a discreteness, will we see signs of it in Hawking radiation? If you treat the discreteness very naively, you find out that the Hawking radiation turns off in something like a light crossing time of the black hole. In other words, no time at all. That's almost certainly not right, but there might be, when we understand quantum gravity better, still observable signatures of discreteness in the Hawking, visible in the Hawking radiation. Also, are there other observable signatures of discreteness? One that many people have, probably has gotten more work than all others, is breaking of Lorenz invariance. And this would be manifested typically in the way people think about it as modified dispersion relations. In other words, light of different frequencies would travel at a different speed, so that, for example, maybe some people have looked at gamma ray bursters, so different photons emitted at different wavelengths from the same event might arrive at different times. From the causal set point of view, there's no hope to have Lorenz breaking. Lorenz invariance will be preserved, but nevertheless, there can be new effects which are completely compatible with Lorenz invariance, which are space-time analogs of Brownian motion. I mean, you might know from the history of physics that the thing that sort of the capstone of atomic physics that put the atomic hypothesis that put to rest all the final doubts about whether there were atoms was Brownian motion about 100 years ago. Well, there can be and this comes from the discreteness, the discreteness of atomic matter, ordinary matter. If space-time is discrete, then there ought to be a kind of Brownian motion associated with that, and because of the Lorenz invariance, it's highly constrained. We call it swerves, and one can look for them. Unlike the, oops, no, I haven't got there yet, sorry. So we can look for them. Finally, let me mention initial conditions for the cosmos. These are the kind of questions that, if you're interested in the origin of the cosmos or the origin of our cycle of expansion, that are very burning questions, which inflation was invented as one answer to the question, but it may not be the right answer. And the question can be posed in different ways. People do pose it in different ways. But I think the simplest way of understanding it is this. If we take the universe as we know it now, and if we just extrapolate everything back by solving the relevant equations of motion, which are the Einstein equations and the relative equations for the matter, the Boltzmann equation, and so on, if you just run it backwards and ask what would it have been like at the beginning, or at one Planck time, 1 Planck 10 to the minus 43 seconds after the beginning, the singularity that you come to if you run the equations backward, you find that although it's only a Planck time old, it's not a Planck radius in size. Its radius is some immensely greater number, which we don't know, but it's at least something like 10 to the 28 orders of magnitude bigger than the Planck radius. And not only that, it's approximately flat, approximately homogeneous, and approximately isotropic to a very high approximation, which we see when we look out at the CMB, so-called the cosmic microwave background. So why did it have this very unusual kind of initial condition? Okay, so I've given a lot of questions here, and now I want to set about saying a little bit about how the causal set program answers some of them and what's its status in general. But since this is sort of a natural break, maybe I should ask if anyone has any question that they want to raise about what I've said so far. Yeah?
What did you mean by holes in space-time? At some point you made a statement.
Yes, holes in space-time. So you could take imagine that this was a space-time manifold and it had some metric on it. Then so a space-time manifold is a four-dimensional topological space. Let me just arbitrarily excise portions of it, like this. So what's left is still, from the mathematical point of view, a manifold. It still has a metric on it, and it's still, the metric that's left will still obey the Einstein equations, right? So, which say, well, let's say it's pure gravity, just for simplicity, then the Einstein equations are this. This is equally well a solution of the Einstein equations. That's what I meant. So it's a space-time with certain portions removed. Yeah?
Is it a good question to ask what is the topology of the universe?
What is the topology of the universe? That's a very good question, yes. I could have certainly added that. So as far as we have no evidence, but people have looked for evidence of other topologies. For example, it could be spatially a sphere, and if it were, you could see multiple images of things, and people have looked for that kind of thing, and so far, of course, not found it. Yeah, so that's, in fact, it's a question that Riemann actually raised, if I'm remembering right, in that same lecture. Okay, so let me, what? These holes are not black holes. These holes are not black holes, although it's conceivable that black holes would produce them, but these could be just artificially produced. The point is that this is just as much a solution of the Einstein equation. What it's not is what's called globally hyperbolic, and there's a general kind of belief that maybe space-time should be globally hyperbolic. That's what's known as the cosmic censorship conjecture. But we don't understand the physical origin of that principle. It's something beyond the Einstein equations. Okay, so let me now say something about the status of the causal set program in relation to those three areas of kinematics. Is there a problem? Relation with kinematics, dynamics, and phenomenology. So, as far as kinematics is concerned, perhaps the most important question is, well, I showed you before a picture of a causal set, and I didn't really explain what the picture was, but what it is, it's a picture of elements, what you might call atoms of space-time, and relations among those elements. And the relation is no more than the relation of before and after. So in the technical mathematical language, it's a binary relation among elements of a set, and it's what's technically called a partial order, that relationship. So the causal set is no more than a specification of certain elements, and which elements precede which elements in this order, and which elements neither precede nor follow each other, which corresponds to the notion of space-like. How can such a rudimentary structure give rise to something like a space-time, which has got a complicated manifold differentiable structure? It's got a metric, it's got a notion of length, and so on. So it turns out, I mean, of course, the claim is that it can, and if I couldn't claim that it could, then the causal set program would be dead at the very inception. And this has been, although the last word hasn't been said, probably this is backed up by a lot of work in which we understand how to read out dimension information from the causal order, information on length, which is by counting, even information on homology groups of spatial hypersurfaces, in other words, topological information. We have ways of talking about the area of a horizon, or an area that is a 2+1 dimensional submanifold. It's both deals. It has still some problems, but insofar as it works, it succeeds for both equilibrium, that is stationary black holes, and also dynamical ones which have just formed and maybe the horizon expanding very rapidly at the speed of light. And then finally, the problem of time. As I said, the problem of talking about what are the observables of quantum gravity, this is essentially solved, and it's literally solved in the context of these classical sequential growth models. As far as dynamics is concerned, there are two aspects to it. One can talk, if one is doing quantum gravity, the full story of quantum gravity, then one is talking about the dynamics of the causal set. But if that dynamics does not of itself produce all the other matter that we have, the gauge fields and so on, then there's the question of the dynamics of the other fields living in a background causal set. So for those who are not physicists, I should say that by background, that's what we in physics we call something background, when it's just postulated, put there, and you study the dynamics of other objects in it, treating it as an arena. So the two big progresses that have happened recently in causal set theory is we have a way of talking about dynamics for a scalar field. So that's both a classical dynamics, when we can write down a wave equation and ask questions about propagation of scalar fields, say from distant objects to here. And then there's also a quantum field theory for a scalar field. which actually gives rise to the kind of developments that Bal referred to, which are actually in the continuum. So we know quite a lot at this stage about dynamics in a background causal set. The other aspect is dynamics of the causal set, in other words, full quantum gravity. And here we have the dynamics of sequential growth, the classical dynamics that gave rise to the picture I showed you in the beginning. And we also have an analog now of the Einstein-Hilbert action, which is what goes into the path integral, would go into the path integral in the continuum for quantum gravity. And it's, interestingly enough, it's not local, but in harmony with the essential non-locality of the causal set, it's a bilocal action functional when you view it in continuum terms. We also have this beginning of an answer to why we recover space-time from a causal set, but only really in the context of special kinds of causal sets which are two-dimensional in character, which is a relatively trivial case, but not... Yes?
What exactly is the relationship between causal set and contrariety? I don't quite understand.
Oh, causal set is the hypothesized deep structure of space-time.
So you just generate the space-time structures of the causal set?
Yes.
Put in the usual, dynamics on it, or?
No, we have to have, so I'll come to that in a little bit, but we have to devise a dynamics for the causal set, which under a suitable approximation looks like looks like the Einstein equations, basically. No, let me postpone that answer for a second. It's certainly not static, no, because in these models it grows, it increases with time. But let me put this here. Here, if I go down 2 slides, this is a picture of a very small causal set. Maybe it'll give you some idea. But the idea is that a causal set is to space-time as a collection of atoms, a collection of water molecules is to an ocean or something like that. Okay? Is it clear? Oh, okay. So the ordering is related. It is time, yes. The ordering relation is time.
It is symmetric in terms of
Is it symmetric? Well, yeah, maybe. What? Yeah, maybe you can raise the question again after I show the next. So at the level of phenomenology, there's a prediction that came out of causal sets, a heuristic prediction some 20 years ago, that the cosmological constant would not be exactly 0, but it would fluctuate. And the magnitude of the fluctuations was given. It turns out to be, at the present epoch, about 10 to the minus 120 in natural units. So unless by some very strange coincidence it happened to be 0, one would expect the observed cosmological constant fluctuations to be plus or minus of this order of magnitude. Of course, that's been seen. So to a certain extent, quantum gravity, I've said, for those who know what this means, is batting 1,000 in predictions, meaning the sign is not predicted. It could have been either one, yeah. The next thing was about the question of why is the beginning of the cosmos the way it is? Why is the early universe? Here we don't have any real, more than a toy model, but it's a very suggestive toy model, in which the answer, it comes out of these classical sequential growth models, and the answer would be, for example, why is the universe so big? The ultimate answer would be because it's so old, because it's gone through so many cycles of expansion and contraction. So in this kind of model, it would have started small, expanded, contracted, expanded. Each time it would get bigger and more homogeneous and isotropic. We also have a model of these swerves, this space-time version of Brownian motion. Unlike the case of lambda, where you actually get a prediction of the order of magnitude, here there's a free parameter in the model, only one for the massive particle. But what you can do is put, so far we haven't seen it, one hasn't seen it, but using the nature of the CMB, one can put very strong bounds on this phenomenological parameter. There's also a model of propagation of light, scalar light, so it's in quotes, along the causal set in which we're trying to see if the underlying discreteness will manifest itself in propagation of a field rather than a particle. So far, unfortunately, when you put the numbers in, it doesn't look too accessible to observation. There's two proposals for black hole. Entropy at a kinematic level, one of them based on this new action functional, which I hope I'll have time to say something about. And then let me finish with this one, which is frustratingly probably the most secure prediction of causal sets, and at the same time the most inaccessible experimentally. But the prediction is that it's like a form of superasymptotic freedom. It's that all scattering cross-sections should go to zero at sufficiently high energies. But what sufficiently high energies means here is around, unfortunately, as you might guess, around the Planck energy. So, just because I'm running late, raise it again at the end, yeah. It would be nicer if there were 4 neutrinos. I won't tell you why right now, but I can tell you why. So let me answer the question which I think has not come across clearly to many people so far, which is what is a causal set? Try to give you a sense of how space-time emerges from that, and then try to indicate at least a little bit of the recent progress, which allows us now to write down the analog of the Einstein-Hilbert action, and which came from thinking about how you would describe a scalar field in a causal set, how we would cope with this radical non-locality, whose origin I would try to indicate in it just now on the next transparency or slide. So first, what is a causal set? So I've said it a couple of times in words. A causal set to a mathematician is a locally finite partial order. Now what do those words mean? First, let's look at a picture of one. The other picture was probably too difficult to see the details. Here's a particular kind of causal set whose elements actually are themselves causal sets, which comes up in the context of classical sequential growth. So don't look at the little pictures inside the ellipses. Those are small causal sets. Just look at this whole pattern of circles and arrows, or circles and lines. This shows, if causal set theory is right, these are, you could think of as the atoms of space-time. And what these lines show is indeed a temporal relationship among these atoms. So given any two, say this one at the bottom and this one here, there's a line here, and you can think of this as a space-time diagram. Fortunately, in mathematics, we use the same, one uses the same sort of convention to represent temporal order. So this fact that there's a line from this to this, don't worry about its color, that's for something else. But the fact that there's a line from this to this shows that this came before this. This lower one precedes this one here. The fact that there's no line between here and here means that there's no relationship. This is what we call space-like. This one neither precedes nor follows this one. There's also no line between this and this, but nevertheless, this lower one precedes the one directly above it, because indirectly, there's a transition from this to this to this. So what this represents is, you can call it the causal order, you can call it the temporal order, you can also call it the relationship of ancestry. And if you think about it, ancestry is a kind of causal order, because an ancestor is a cause of the descendants. And this has what people call a partial order, has precisely the properties of ancestry. In fact, a locally finite causal order. So if this is me, say, and this is my mother, then my mother is my ancestor. And this is her mother, let's say, then that's my grandmother, who's also my ancestor. And it's always the case that an ancestor of one of my ancestors is also my ancestor. In technical language, this is called transitivity. So a partial order is a transitive relation. In addition, it's also the case that I'm never my own ancestor. In technical language, this is called acyclicity. In the temporal language, it's saying that you can't travel into the past. There are no closed causal curves. This is also part of the definition of a of a partial order. And then there's discreteness. I haven't drawn a whole continuum of these, just a finite number of them. It goes up to the future, if you like, indefinitely. But in the context of cosmology, we can always assume that it goes to the past only a finite amount. So no one has more than a finite number of ancestors. This is the discreteness. And that's mathematically the definition of a causal order. Now you might add, so I hope a partial answer to your question, but there's also the question, what has it got to do with space-time? The answer to that is meant to be in this conceptual equation at the bottom of the screen, which is geometry equals order plus number, where the number is actually representing the volume of a portion of space-time. So every portion of space-time is deep down a causal set. If you want to know what, if you arrange some light rays and clocks and rulers and so on and measure the volume of a region of space-time, what you're really doing indirectly, according to this hypothesis, is counting the number of causal set elements that compose that region. So how do we get out of space-time? Unfortunately, I can only indicate it sketchily, but let me say it in this way. Space-time emerges. Let me put a little flesh on the bones of this slogan that geometry is order plus number. The question is, in what sense, if you ask how does a space-time emerge, another way of asking that question is in what sense can we say that a given M, a space-time manifold M, which is a Lorentzian, which is a manifold, it has a metric on it, the metric has a Lorentzian signature, in other words, it has one time-like direction, and all the rest space-like. In what sense can that kind of elaborate mathematical structure serve as an approximation to a causal set, which is a partial order? This is something like asking, in what sense giving a collection of atoms, say 10 to the 123 atoms, and giving the locations of all the atoms, in what sense can we describe that just by a simple profile, some density function? It's not, that's a question you come up all the time, if you're across all the time, if you're trying to derive, say, the Navier-Stokes equation. But it's not a very deep question in some sense. It's obvious how to proceed. In the case of, if the atoms are uniformly distributed with an approximate density of rho in some region, then you just call that the density. It's much more subtle in the case of a Lorentzian manifold because of this minus sign, because time is not the same as space. But the answer that can be given is that a manifold M is a good approximation to a causal set C, something like this picture here, if the manifold contains within itself a set of points. Remember, manifold is just a space-time, so it contains within itself a set of points that are isomorphic to the causal set. They have the same causal order, and which are uniformly distributed with a density which is 1 in natural units, which is the Planckian density. This is the definition. It turns out that if you want that to be true, there's a subtlety here in the meaning of uniform distribution, which, as I said, is related to this minus sign here, which tells you that, in fact, a crystalline or a regular set of points cannot satisfy this condition. What can satisfy it, and the only thing we know can satisfy it so far, is an irregular or more or less random set of points, technically a Poisson distribution. So in this way, causal sets answers one of the questions I raised before. If there's discreteness, is it crystalline or more fluid-like? The answer is it must be fluid-like. And once you do that, these distributions we call sprinklings, once you do that, you automatically respect Lorentz symmetry. I will not, there's a theorem here that if I had a little more time I would read to you and explain, but what it says in words is that the probability that a causal set that's well approximated by a portion of Minkowski space will break Lorentz invariance is 0. So we should not be looking for Lorentz violating phenomenology of causal set. So what I want to do is not quote a theorem, but I want to give you, because it's one of the basic facts about causal sets, I want to give you a sense of how that Lorentz invariance comes about, and also how it's related to the essential non-locality. Okay, so here's a picture of a causal set, or it's more precisely, it's a set of points within a two-dimensional Minkowski space, which mirrors, is isomorphic to some causal set, as I said. So this is just basically a sprinkling or a random selection of points in the two-dimensional Minkowski space. I haven't drawn in here the order relation, so I haven't drawn in here these lines, which you saw here and which you saw in the picture that I started with, but you could imagine drawing them in yourself. They're here, the light cones here are at 45 degrees, so any elements which are within the 45-degree quadrant of another element are to its future. And here, but what I want to try to illustrate here is the Lorenz invariance. So here's a blow-up, here's a little square within this, and here's a blow-up so you can see more clearly how the points are distributed. And you can see it's just a random distribution of points. Now what happens if we perform a Lorenz transformation on this? Or what if we, so to speak, view it from a rapidly moving reference frame? Well, a Lorenz transformation in 2 dimensions is just a linear transformation that squeezes everything down in one direction and stretches it out by the same amount in the other direction. So it turns this square into a parallelogram that you see here. Now let's look at a little square of the same size. It looks smaller, but the scale of the axis is different. So let's look at a little square of the same size and blow it up here. And what do we see? Well, if you're sitting close enough, you probably will be able to detect that this is not literally the same as this. On the other hand, if you don't look too closely or you're not sitting close enough, you really, I think, won't see any difference. That is, the boosted causal set is no different from the, so to speak, causal set at rest with respect to some lab frame. So it's in this sense that the causal set is Lorenz invariant, and this can be made as a precise, very strong mathematical theorem. So in relation to this picture now, we can also see another thing, and specifically in relation to Lorenz invariance and discreteness, we can see another thing, which is the radical non-locality of the causal set. So what is a very general statement is that you can have discreteness, you can have locality, and you can have Lorenz invariance, but you can't have them all. Right? So if you're going to have discreteness, as we have with causal sets, and you're going to have a Lorenz invariance, as I've just shown you, you cannot have locality. This can be actually understood in a fairly simple way from this picture, which I've shown some elements of the causal set, could be some elements of this sprinkling. So now, and if we ask ourselves, what is the meaning in a discrete setting of locality? If you think of the Hubbard model that we heard about yesterday, I think it was mentioned that you can't really have locality in a discrete structure, but you can do almost as good as that, almost as well, by having just nearest neighbor interactions. So you might think in a causal set, we'll just have nearest neighbor interactions. The problem is, how many nearest neighbors are there? In a kind of spatial lattice that we're used to, like in the Hubbard model, you just have a small number, order 1 nearest neighbors. In the case of the causal set, you have an immense, even in an ideal limit, infinite number of nearest neighbors, and this is precisely because the non-compact character of the Lorenz group. So here's an element. Suppose this is a nearest neighbor, so we could think of it as situated at a short distance into the future of this one. But remember, distance is a Lorentzian, it's a Minkowskian distance. It's got this minus sign. So anything along this light cone is actually at 0 distance from this point. In particular, say this element is also at a very, not on the light cone, but very small. It's no farther than this element. So if this is a nearest neighbor, this has an equal right to be a nearest neighbor. This also, and this also. And in general, you get a huge number of nearest neighbors, which in some given reference frame are nowhere near. They're far nearest neighbors, right? They're nowhere near the element that you wanted them to be near. This is what I meant by a radical non-locality. The question then is, how can we recover any local physics at all from this kind of setup? And I want to finish by briefly reviewing how we've been able to do that for a scalar field and how it led to this expression for the Einstein-Hilbert action. So don't worry about this. What are we looking for? So we have a causal set, which is a collection of elements we can think of it as approximated by some region of Minkowski space, for starters. So we then deal with the subset of Minkowski space that's isomorphic to that causal set, which we call a faithful embedding of the causal set. We imagine a scalar field on the Minkowski space that induces on each element a number. So a scalar field on a causal set is then just attaching a scalar number to each element of the causal set. However, suppose we wanted to write down a wave equation for that. You know, the equation that this is the wave equation for a massless scalar field, which if we translate it into coordinates is partial squared phi over partial t squared plus partial squared phi partial x squared plus, and then the z1, that equals 0. To write that equation, or some analog of that equation, we need to know how to define this D'Alembertian operator, this box operator. How can we, that box operator is local. It only looks in the infinitesimal neighborhood of the point where you're trying to evaluate it. How can we do that in a causal set? What would it mean? So first of all, how would we describe the scalar field? Just by a list of the values at the different elements, a vector as you might call it, in the computer sense of vector. And then we need a matrix, box jk, or here it is, which when we apply to that vector gives a good approximation to the D'Alembertian. The following, it turns out, for many years I thought this was actually impossible, but it turns out that the following works. I'll just briefly describe it to you. The matrix has on its this is a two-dimensional version. The four-dimensional version is only slightly more complicated. So it has on its diagonal -1/2, and for any other two elements, it has a number which is either 1, -2, or 1, where that depends on, in some sense, the causal distance between the two elements. If the two elements are immediate neighbors, nearest neighbors, then it's 1. So that's like one being the child of the other. If it's like one is the grandchild of the other, then you get -2. And if one is like the great-grandchild, then you get 1 again. And otherwise, you get 0. So that's a very simple expression. And in a continuum limit, it can be proven to reproduce the D'Alembertian. One parameter generalization of this is available, which is useful for certain purposes, but more complicated. And so now, this is the last slide. And so in a curved, what I told you here was for flat space, but I want to see how it gives rise to the scalar curvature expression, the Einstein-Hilbert action. So this was for flat space. It can be proven to reproduce in an appropriate limit the D'Alembertian of the scalar field. But in curved space, you might expect there to be curvature corrections, and in fact there are. And you can use the same expression, but what it produces is not just the D'Alembertian of the field, box phi, but also that D'Alembertian plus or minus 1/2 times the Ricci scalar. At least we know this up to dimension 7. It's presumably true in all dimensions. Well, if you have this expression, D'Alembertian, say in 4 dimensions, minus 1/2 the Ricci scalar, and you apply it to the function -1, the D'Alembertian will give 0, and you'll be left with just the Ricci scalar. You can then add that up over that Ricci scalar up over all of the elements of the causal set. That corresponds to integrating the Ricci scalar, because remember, number equals volume, so if we sum it up, we get the volume. And in the special case that I showed you here, this is an extremely simple expression. You're just looking for certain subcausal sets of this big causal set, these parent-child ones, these grandchild ones, and so on. These subcausal sets like this, and you just count how many there are of each sort. They're like elementary building blocks in a sense, and you add them up with these appropriate coefficients, and that gives you the analog of the Einstein-Hilbert action. And then one thing we're doing now is trying to use this in Monte Carlo simulations to see what comes out, and I think that's a good place to stop.
I think, Shyam?
A couple of small questions. First, your coset is a subset of points in the given space-time?
No, it's
an abstract set.
Inherently it's an abstract set.
If it is abstract set, do I have a situation wherein there is an element which has no ancestors?
Yes.
Always?
No, only if you assume it. You need not assume that. The only thing I think you really need to assume is called local finiteness, which is that between any two elements there are no more than. So in other words, given any two elements, the number of elements which are a descendant of one and an ancestor of the other is finite. So so you haven't packed an infinite number of elements into a finite time interval, so to speak. But there's no need a priori to assume that there's a finite number of ancestors. However, in the context of the sequential growth models, we do assume that. And so it's like a cosmological model which has a built-in beginning. And then there'll be at least one element that has no ancestors, like if this were the causal set, so on. There'd be only one, this would be the only one without ancestors, but you could also devise ones like this, which would have two elements without ancestors. Technically, they're called minimal elements of the causal set.
Thank you.
Yes, a question.
Yeah.
Can I characterize this as a novel discretization of quantum gravity? A lattice formulation of quantum gravity?
Well, lattice, the only, I would say that that's true in the context of dynamics in a causal set. Remember, like the dynamics of the scalar fields we saw here. If we're talking about dynamics of a causal set, I guess that terminology might be slightly misleading because discretization suggests that there's some continuum there, and we've made it discrete, maybe by, some sort of process of selecting a subset, a lattice, or some latticization. But as it came up in the Shyam's question, I think that we think of this as an abstract object. I mean, it's concrete in the sense it's meant to be space-time, but abstract in the sense that it's not tied to any particular continuum. So in this growth process, what happens is the elements are born one by one, and they build up, sort of by accretion, so to speak. They build up this causal set. And this process presumably is still ongoing, because the future is still coming into being. And that's not happening in any space-time. So it's discrete, but I don't think I would call it a discretization. However, it can be used in that way. So if you're only interested in flat space-time, but you would like a Lorenz invariant cutoff, which many people would like, then you can use the causal set, because I showed you. So I think it can be used in that way, but if it achieves its full potential, then it will go beyond just being a discretization of something. It'll be an object unto itself with its own dynamics.
So can I view the causal set as atoms of ether?
Sure.
Thank you.
You will be giving a seminar on Monday, if I am correct, at 10:30, right? Okay. Rafael is giving a seminar on Monday.
Is it?
I believe so. Somebody said.
I could, but
I remember those guys are asking.
let's say provisionally, tentatively. It's still in the future.
There is Jan was asking a question. Somebody behind, I can't see.
Yeah.
Okay. Then maybe here and then we stop. Because of time.
Yeah, if you replace our conventional here,
Oh, there you are.
if you replace our conventional concept of space-time with causets as you are doing,
Yes.
could you please comment on what would happen to A, the classical tests of generativity, and B, what happens to the flat space limit, namely special derivative?
Well, I'm not sure I can comment beyond what I said already. So, the first thing is, of course, we must reproduce those. So it must be that, and this is the key question that every theory of discrete quantum gravity, in fact, I think every theory of quantum gravity probably has to face, which is why does it produce something that resembles the space-time that we know and have around us? if we can do that, that is, if the causal set has a dynamics which leads it to produce the kind of causal set which is well approximated by a space-time, then you have an emergent space-time. It should be said, just to give indicate how difficult that problem is, that the vast majority of causal sets in no way resemble space-time. So those which do resemble it are very special. However, the ones that arise by sequential growth are also very special. So, but what I'm saying is if you just pick at random a causal set out of a bag, you'll get something that only lives for 3 Planck times, basically. Looks nothing like a space-time. But once you put dynamics into the story, it can look like a space-time. If you've done that, and if the effect, then you expect an effective theory, and then let's say it's described by an effective action. If that effective action is local, then dimensional arguments that are common in renormalization group kind of discussions show you that you'll basically just get the Einstein equation. Except, as usual, you might get too big a cosmological constant based on the dimensional arguments. However, I tried to argue that if you did that, you wouldn't even get to space-time. Because if you get a large cosmological constant of Planckian magnitude, you get curvature Planckian scales, and then that doesn't make any sense in a discrete structure which is itself of Planckian scale. So if you can get a manifold out, then I'd say the rest is almost easy sailing. You'll get some version of the Einstein equations, and therefore you'll produce classical general relativity, and that includes, as a special case, Minkowski space. Then you might ask, what deviations can we expect to see from that? That'll be the interesting phenomenological question, and I tried to refer to some of those in the talk. My own feeling is that the cosmological constant, or what people call dark energy, or more observationally, the accelerating expansion of the universe, is one of those indications. Well, we're looking for ones that are well approximated by space-time. But maybe I could give you, the only axioms were the 3. It was transitivity, which is that x precedes y, pz. Okay. That's the descendant of a descendant is also a descendant, right? That's transitivity, it's called. And the other one is acyclicity, that it doesn't happen, how do we say this? Not x precedes y and y precedes x. And then there was the discreteness, which is that, if I write it out as a formula, it's just the cardinality, in other words, the number of elements which lie causally between x and y. What have I done? Yeah, that's it. That the cardinality is finite. So that's the strict definition. However, you might be asking another question, which is another key question, which is how can we recognize? I've argued that a causal set can resemble a space-time or vice versa, but how would we recognize when it's actually resembling a space-time? That's a much harder question. But in one particular case, there's quite a simple answer. That's the 2-dimensional case that I referred to along the way. I don't actually remember specifically what it is, how it goes now, but there are causal sets we call 2-dimensional if you can find isomorphs of them within 2-dimensional Minkowski space, M2. And it's much like these graph theorems. There's a couple of bad causal sets, which subcausal sets, if you find them, then it won't be, in this sense, faithfully embeddable in 2 dimensions. But if you rule them out, then you get what are called 2-dimensional orders in mathematics. Strictly speaking, what they are is intersections of 2 linear orders. That's the definition of a 2-dimensional order. And now we can ask, among all the 2-dimensional orders, what do they look like? How many of them are well approximated by space-time? And the interesting answer is, this is just an entropic fact, the interesting answer is that when n becomes large, with very high probability, they look almost like a portion of flat space. They're very close to being like a portion of flat space-time. So you have flatness and manifold-like property and somehow emerging. Another one, I'll just mention this because it's somehow related. it's suggestive, although I don't know exactly what it suggests, but it's suggestive, is that suppose we take a causal set which represents a portion of space-time, which is well approximated by portion of space-time. You take any two elements in the causal set, and now you ask, let me choose completely at random a chain between them. In other words, a succession of elements, like ancestors, like child. It doesn't even have to be child, but a suggestion. So completely among all possible chains that run from one to the other, choose one completely at random. With high probability, you'll get one that's extremely close to a geodesic between those 2 points. So it's almost like a law without a law, but so it's suggestive, as I said. But in this case, the analogous statement, which is a little harder to state, gives you 2 dimensions. If you go to higher dimensions, a simple characterization of which causal sets are like space-time is still very much an object of inquiry. But although there are some ways, there are some tests, but no simple criterion.
I think two more questions. Can I stop?
There was a...
I gave him that gentleman behind.
Yeah.
And
okay, so
yeah.
Yeah, I'm not sure I completely understand. So how this in this causal net framework do you represent entanglement?
Entanglement. Well, if I referred to entanglement, which I think I might have at some point, I was referring to this scalar field theory on a causal set. Okay, so in that case, if we wanted entanglement, is that the context of your question? Like, suppose there's if you want entanglement of the causal set itself, you mean it in the quantum sense of entanglement, right? Then, of course, we'd need the quantum theory of the causal set, and I don't know exactly how that would go. But there's actually a nice answer if we talk about entanglement of a scalar field on a causal set. So here's this, again, this causal set. Scalar field would be at each element of the causal set, there's some value phi of x, let's say. Now we have to make that into a quantum field. Then, of course, entanglement is relative always to a quantum state. So we have to have some state for this quantum scalar field. And then you can actually do something very nice. One normally thinks of, so here's a picture of, say, a black hole, kind of black hole space-time. What do I want to do? Okay, so here's, for example, a picture of a black hole space-time. Something like this. That's a better picture. Okay, so here's the inside of the black hole. Here's the outside of the black hole. We can take a portion of the space-time. Maybe I should say where I'm going. I'm trying to show how to express entanglement in a space-time way. So we can, if we ask for the entanglement of the state, say along this Cauchy surface on the then we would normally think of dividing it into 2 portions, inside the black hole and outside the black hole, tracing out the variables associated with the inside, getting an effect of reduced density matrix for this. That doesn't work well in a causal set. But what does work is you take a whole space-time region, and it turns out, at least in the context of a free Gaussian field, that you can define a notion of entropy of a space-time region. It's just a quite simple expression in terms of the Whiteman function, it turns out, which is the 2-point correlation function. And we can directly do that on the causal set. So once we have the scalar field theory on the causal set, we can take a region which would correspond to this is the future domain of dependence of this portion of the Cauchy surface on which we wanted the entanglement entropy. And we compute the entropy of this region, and that should give the entanglement. So right now we're doing some numerical evaluations. So far it's looking a little peculiar, I must say, but hopefully it'll come into agreement with the other expressions that one has.
I think we should stop this session because we are running over time in a gross way. So let us stop.